We're coming to the end of this course. So today we're going to have our last class. So we will first complete the discussion on the applications. We still have a small part left from last class. We'll go through that part very quickly. And then the second part of today's class would be the application issues. Remember, we had one part left. Other than the power semiconductor devices, power converters, control techniques, and applications, we still have a chapter which is called the application issues of power semiconductor devices. That is a very short part of the material. So that's the second part we're going to cover today. And then finally we will make a review of this course. So that's the arrangement I currently have for today's class. From last class we have started to talk about applications of power converters in utility system, electric utility systems. If you still remember, I mentioned there are three major application areas. One is motor drive, one is all different kinds of power supplies, and the third one would be the applications in utility system. We have covered in the last class some of the applications in utility power system already. We talk about HVDC. We talk about reactive power compensation. And we, as I remember, we were here last time, harmonic suppression. Harmonic suppression based on power converters. Harmonic suppression. If you still remember, last time we mentioned there are two basic types of solutions to deal with the AC side, input harmonics, input current harmonics. One is to reform the input stage of a power converter. Usually the input stage is AC to DC power converter. Okay. That is called power factor correction. That is one solution. To reform the AC to DC power converter so that the AC input current does not contain too much harmonics. The input current would be very close to a sine wave. That is one solution. The other solution is to add extra filter. To add a filter to eliminate the harmonics. If you still remember, let's see, if this is the AC power grid, this is the inner equivalent impedance of the grid utility. Okay, and then this is, let's see, this is the original power converter. if this power converter is generating, let's see, current like this. This is what we call 120 degrees current waveform. This is what's the typical input current waveform from a three-phase bridge rectifier, thyristor rectifier, with inductive load, when this inductor in the DC side is large enough. So usually what you have is this kind of current at the AC side. Okay? Now I want to eliminate the current harmonics in the current flowing into the AC utility source. What I do is I can use a filter here. Let's say the traditional filter is an inductor in series with a capacitor. That's the traditional filter. When I put a filter here, then the current, the AC current I generated from the rectifier. Let's see, this is a rectifier. AC current. This current will actually separate it into two parts. One part is flowing into the utility. The other part will be flowing through this filter branch. So as long as I set the value of this inductor, filter inductor, and the capacitor so that these two are in series resonance, at the harmonics frequency. As long as I set these values at this series resonance at harmonic frequency, then this LC filter branch impedance, total impedance, will be very small. If you still remember, when the inductor and the capacitor are in series resonance, then the total impedance of this will be very small, nearly zero. That's the ideal case. And therefore, for this harmonic frequency, for the current generated by the load, by this rectifier, at harmonic frequency, this branch impedance will be very low, much lower than the impedance of the utility source. Therefore, most of the harmonic current will be flowing through this branch. And very few will be flowing, very small part will be flowing into the utility source. And therefore, all the harmonics will be, if I set this LC filters correctly, then all the harmonics will be flowing through this filter, and only the fundamental frequency component will be flowing into the grid. And therefore, for this grid, this value, this current IS will be having almost no harmonics. So that's our purpose. So that's the basic principle of the traditional LC filter, to eliminate harmonics. That's the traditional one. Now I want to use a more active solution. I'm still connecting a filter between the source and the load in parallel, okay, still in parallel. But the difference is that I now change this LC filter into a controlled current source. Okay, controlled current source. This is realized by a power converter. I can control a power converter like a controlled current source. And I control this current source in this way. I control this power converter to generate current only at harmonics frequency. Okay? I generate that harmonic current at the same amount, with the same amount of the load harmonic current. Okay? Same amount, but in reverse direction. And therefore, the total current flows into the source will be having only the fundamental component. The harmonic current will all be canceled out between this filter and the load. So that's the basic idea of this power converter. This power converter is then called active power filter. That's called active power filter. Well, that's the basic operation principle. As you can see from here, if this is the upper side waveform is the, let's see, this 120-degree waveform is the original AC side current generated by the rectifier. This load is a rectifier with inductive DC load. Then this AC side current of this rectifier with this will be this 120-degree square wave. What I do with this active power filter is that I can measure the how much harmonic current is inside this 120-degree harmonics. So this is 120-degree current waveform. So the second waveform is exactly the harmonic current, harmonic component within this 120-degree current. I detect that, and then I control this power filter, power converter to generate a current IC. This is the current I generated through this power converter. And this IC will be exactly equal in amount to the load harmonic current, but in the reverse direction. It is equal to minus ILH. ILH means the harmonic current in the load current. And therefore, if you add these two currents up, these two currents add up, that will be IS. You add these two up, IS will be these two right-hand side add up together. This harmonic component will be canceled out with each other. And only this fundamental component in the load is left. So in the source current, the current flows into the utility grid. There's only fundamental component left. So that's the operation principle of active filter. Very similar to passive, very similar to traditional LC filter. But what do you think is the benefits of this active filter? Why using a power converter instead of LC filter is better? Why an active filter is better? You have any idea? Why this is better than this one? Why the right-hand side, this active filter is better than this one? What?
We can control. Actually, we are free to control our frequency.
We are free to control this frequency here. Well, in many cases, this load frequency might be changed. Okay? The harmonics inside the load might be changing. Okay? But this value of inductor and capacitors these are fixed. Once you design it, then you install that, and those are fixed. So those can only be effective to the resonant frequency harmonics. Those frequencies are fixed. So once this, let's say the IL fundamental component plus IL harmonic component, when this is changing, when the frequency of the harmonics is changing, this one does not have the original effects I want. Okay? But this one can follow that change. No matter what frequency you are changing to, I can always generate the same frequency of harmonics as the load. Okay? So that means I have the ability to track, to follow what kind of frequencies that the load harmonics have. Okay, that's the first benefit. I can always track the harmonic frequency, no matter what frequency you are changing to. And the second one is, there will be a lot of harmonics in the load, a lot of frequencies, harmonics. So in order to eliminate those different frequencies harmonics, I have to have all different LC filters. Let's see, for fifth harmonics, I have to set a filter. For seventh, I have to set another filter. Okay, 11th, 13th. Okay. So for different frequency harmonics, I have to set different LC filters to eliminate that frequency of harmonics. That's for passive filter. But for active filter, it's not necessary. I can only have one power converter here. No matter how many frequencies harmonics you have in the load, I just detect it at all. Detect those harmonic current as a total harmonic current here. The total harmonic is ILH. Then I generate one current here in the same amount but reverse direction of that ILH. Okay? And I can deal with all the different frequency harmonic current. Okay? So that's the second good solution. Second benefit for the active filter. So because of that, those benefits, so active power filter is considered as a much better solution for eliminating the AC side current harmonics. Okay? But of course, right now, active filter is a little expensive, more expensive than passive filter, because we are using a lot of power semiconductor devices, and this is usually expensive. But gradually, with the development of technology and the availability of a large amount of power semiconductor devices, the relative price of active filter will be decreasing, but the relative price of the passive filter will be increasing, because passive filters is consuming materials like iron, okay, copper. Those materials are always increasing. The price of those materials is always increasing. Okay? So those, let's see, the power filters, that's the basic ideas of power filters. Again, as I mentioned, there will be a continuing course in the future in the graduate level, talking about different power active filters, and also different power converters to deal with different power quality problems. Okay. Harmonics is only one power quality problem. power quality means the quality of the power the utility is supplying to the load. Okay. That's the traditional sense. Usually the load will require sine wave voltage, okay, with constant frequency and constant magnitude. That is the usual requirement from the load. We require that the utility is supplying electric energy like that. Okay. But if there is a lot of harmonics, okay, if there is a lot of harmonics generated into the utility source, that harmonic current will be causing a harmonic voltage drop on this impedance, equivalent impedance of the utility. That harmonic voltage drop adding up to the original utility voltage source will cause the harmonic voltage between these 2 points. So when you have harmonic voltage between these 2 points, the other load, okay, if I have a load here, another load here, let's see, and this load will see this harmonic voltage. That will cause the quality of the power that is receiving by this load is not good. So harmonics is the primary, right now, the primary reason of bad power quality right now. Okay? But it is not the only reason. So if you look at the power quality, current harmonics is not the only reason that causes the power quality problem. There's also a problem caused by reactive power. If the reactive power is not well controlled, then the voltage in the future, you will know, in the power system, if the reactive power is not well controlled, then the voltage magnitude on this utility transmission line will not be very well controlled. The voltage magnitude might be exceeding the normal operating range, or it might be lower than that normal operating range. So reactive power is another issue we have to look at when you deal with power quality. And third one is voltage sag. Voltage sag. Sometimes it is also called voltage dip. Voltage sag or voltage dip means the utility voltage is dropping to a lower level for a short period of time. So if you look at the utility voltage waveform, it is something like this. So during this short period of time, this voltage magnitude is dropped below the normal magnitude range. That's called voltage sag or voltage dip. That is also not good. Okay? Because when the user sees this voltage sag, then this may cause the sudden interruption of power supply, and therefore the equipment might be turned off. And in many cases, this is very harmful. This is going to cause a large loss of energy or loss of material for the factory for a user. For example, if this user is a continuous production line in the factory, and because of that short period drop of voltage, the whole production line will be shut off. And in many cases, this continuous production line cannot be shut off. Once you shut off, then all the material on this production line will be wasted, will be no use. And it takes much longer time, or takes a lot of money to restore this production line and make it reproductive. The basic example, the very typical example of the bad effect caused by voltage dip is semiconductor industry. Semiconductor industry. In the semiconductor industry, you always have this continuous production line, especially the production line to produce silicon, to make pure silicon or to make the silicon chips. This is a continuous production line. Once you lose power for a short period of time, then all the production line will be shut off. And all this material along this production line will be wasted. Okay, that is a lot of money. Okay, so this is another cause. Voltage sag is another major cause of power quality problem right now. Okay, and the fourth one that is very often seen as power quality problem is what we call voltage flicker. Voltage flicker, in which the magnitude of supplying voltage is oscillating. The magnitude is for sometimes low, sometimes higher, lower, higher. This is called flicker. When this happens, all these lines will be for some time lighter, for some time it is the magnitude, the strength of the lighting will be smaller. Lighter, smaller, lighter, smaller. It's just like flicking. So that's why it's called voltage flicker. So you can sense that flicking. This is also not good. Okay? This is not good for the usual electric power equipment. So these are all the power quality problems we have to deal with, and all these things can be dealt with through a certain power converter. Okay? If you use power converter to deal with harmonics, then that's called active power filter, and we can use, we already mentioned that, static VAR compensator or static VAR generator to deal with reactive power. Okay. And you can use another power converter which is called dynamic voltage restorer to deal with voltage sag. I will not get into detail, but you just hear about the name, and in the future you will have a chance to look into details. It is also power converter to mitigate this voltage sag problem, so that make sure the load will always see this constant magnitude voltage. Okay. Of course, we can also deal with voltage flicker, and there's another equipment based on power converters which is called universal power quality controller. Universal power quality controller. And actually, this universal power quality controller is not only able to deal with voltage flicker, but also many other power quality issues. Because it's called universal, that means it can be able to not only deal with voltage flicker, but also voltage sag, reactive power, current harmonics, everything, almost everything. And you can imagine in that way, in order to deal with all these things, then you have to have more converters. So actually this universal power quality controller actually has 2 combined power converters, each one dealing with some of these listed here. Okay? And if you extend this idea to the whole utility system, not at the load side, not only at the load side, but also transmission line, at the distribution line, the power converter, power electronics can also do a lot of things there. Okay? The basic idea is if you look at this power electronics, all the power converters, the reason why power electronics can be very widely used in power system, as I see, there are 2 basic reasons. 2 basic reasons why power electronics or power converter can be applied to power systems. One basic reason is that power electronics provides us with a very fast and precisely controlled switch. Before power electronics, then the switch that we have for utility system, for power system, is only this mechanical switch. Mechanical switch is slow. Okay? It takes time from you send the control signal until the actual switch has actually been turned on or turned off. Okay? That's slow. But we can use power semiconductor to be acting as a switch. Thyristors, a pair of thyristors connected in anti-parallel mode. Okay? That is much faster than mechanical switch. And also this switch is also very precise, can be very precisely controlled. We can exactly control at what time we trigger thyristors. But mechanical switch, we cannot do that. Okay? That is the first reason. With this fast and precisely controlled switch, this is actually originally all based on power semiconductors. Okay. These power semiconductors can be acting as fast and precisely controlled switch for the utility system. This is much better than traditional switches. Second, with PWM control technique, we can actually we can actually provide power sources with any kind of voltage or current waveform. If you still remember the operation principle of PWM technique, we can always generate whatever kind of waveform you want to generate. Okay, that waveform could be voltage, could be current. Okay, this thing never happened before power electronics. Before actually this power converter can be able to do this. Before that, no technique can provide us with that capability. Right now, we have this capability. We can provide any power sources with any kind of waveform. That is very good for utility system, for the power system. Okay? Just like here, active filter, we are actually generating we are implementing a current source that's generating harmonic waveform. And this harmonics is exactly in the same amount of the load harmonics, but in the reverse direction. Okay? That way we can achieve very good result, filter result. Okay? We can generate reactive power, right? With a power converter, we can generate reactive power, and that reactive power can be either inductive reactive power or capacitive reactive power. Any kind of reactive power you want. Okay. These are the two major reasons why power electronics can be very widely used in a utility system. So either in transmission, if you look at the, I'm not sure whether you have this idea already or not. If you look at the power system or electric utility, then you usually have four stages of the system. First, you have to generate. Go through the generation. And once you generate the electricity, you have to transmit. So it goes through the transmission stage. You have transmission line. Transmit that power from one place to another place. So once you reach the place you want, you have to also distribute. So you have distribution line. Okay? And finally, this power will be reaching the load. Okay? So then load can be utilizing that energy. So that's utilization. Okay? So from generation, transmission, distribution, to utilization. These are the four stages for the power systems. And power converters can be applied not only to utilization. We can much better use that energy, but also can apply to transmission system, distribution system, okay, and even the generation system. Okay. So power converters can be applied to all the different stages of power systems. If this is applied to a transmission system, there is a special name, which is called flexible AC transmission system, or in acronym, FACS. Okay. So FACS is actually a general term of applications. If power electronics, application of power electronics to, I'm sorry, there's a typo here. FACS is actually a general term of applications of power electronics to the utility electric power transmission system in order to achieve higher controllability and larger transmission capacity. So with the help of power electronics, we can achieve higher controllability and also larger transmission capacity. Okay, that is the FACS. Again, I will not get into details. There is a lot of equipment or devices based on power electronics. Okay, we have mentioned these two already, SVC and SVG, but there are many others. Okay. To help transmission system to achieve higher controllability and larger transmission capacity. If power electronics is applied to a distribution stage, there's also a special name. People call that custom power technology. Flexible AC transmission, that's the short name, special name for transmission applications. That's FACS. And power converters applied to distribution system, that's called custom power. Okay. flexible AC transmission, custom power, technique. Okay? Again, this idea of custom power is exactly a general term of applications of power electronics to utility distribution system for better quality of power and higher reliability of the power supplying to the different loads for different customers. Okay? There are many different types of power converters we can apply to distribution stage. We mentioned these two, SVC or SVG, or APF, active power filter. Dynamic voltage restorer is used to deal with the voltage sag problem, and many others. Okay? There is a solid state transfer switch. This is used as a switch. This switch is realized by thyristors, always realized by a pair of anti-parallel connected thyristors. That will also provide us with better quality of voltage and better reliability, higher reliability of the power. So there will be a lot of detailed discussion in a continuing course about this custom power techniques. Generation. Traditionally, power electronics is not very widely used in generation. But in recent years, because people are thinking about to use a lot of alternative energy sources, like the energy from the wind, energy from the sun, okay? Then in this case, power converters has to be used. They have to be used in these cases. Because for wind power, if you have a generator to convert a wind power to electricity, then you still need a power converter to transfer that, to change or convert that electricity into the energy that you can connect to the utility grid, or you can supply to the user load. So you have to go through a power converter again. Okay? For solar power, for the electric energy generated by the photovoltaic solar array, that is usually DC energy. Okay? And in order to be connected with the AC utility grid, or in order for the load user be able to use that, then you have to have DC to AC converter to connect that DC energy with the AC network. So you still have to use DC to AC converter. Okay? So that's two typical examples. So a lot of alternative or new energy sources, the electricity they generated has to be converted through power converter to the form of electric energy that can be interfaced with utility grid or be utilized by the user. Okay? So therefore, in the generation stage, you also need power converter. In the generation stage, a lot of more and more power electronics has to be used. Okay, so you can see right now a lot of our graduate students are actually working in this area, in the developing different methods, different techniques to interface the new energy sources with utility grid or with the user loads. Okay. There are other applications. Lighting is one example. Okay. Traditionally, all these lights, they're just turn on, turn off without power converters. Okay. These are directly connected to the grid. But gradually, a lot of new lighting sources are coming out. Okay, you have LED, okay, light emitting diode, LED. For LED lighting, in order to drive those LEDs, you also need power converter. Because LEDs can only be driven to work under certain form of electric energy. You cannot drive that to work with the traditional AC grid voltage. Okay? So you still need power converter to drive that to light. Okay? And also this, even if it's not LED, I believe these lights right now are also driven by a power converter. This is what we call electronic ballast. The traditional fluorescent lamp is driven by a traditional ballast. Traditional ballast is just using an inductor and a switch, okay, to generate that high voltage so that this fluorescent lamp can be turned on. And gradually, people found out that this traditional ballast with this large inductor is wasting a lot of energy. The efficiency is very low. Okay? And then gradually people find out that we can use electronic ballast. This electronic ballast is actually just a small power converter. A small power converter to transfer the original, let's say, 220 volts and 50 hertz voltage from the utility grid to a certain high voltage, high frequency voltage that can light, that turn this fluorescent lamp, turn it on. That's called electronic ballast. So it is actually a power converter to provide voltage waveform that can turn the fluorescent lamp on. And therefore, that electronic ballast can achieve very high efficiency of operating, and with even better performance of the lamp. Okay, so lighting is another very widely used power converter area. Okay, welding, another application. I will not get into detail. Lighting, welding, a lot of different applications. All right, so that's what we want to cover for applications. So in the next class, we will be go through the application issues for power semiconductors very quickly and do a very brief review of the whole course. So take a break.